This is Fisher Yu. Today I'm going to talk about deep learning for supervised learning tasks and how we can use deep learning techniques that you learned in the previous two lectures in various things in computer vision. Or in my title, I'm calling it deep learning for everything in computer vision. So to be more precise, when we talk about deep learning for computer vision, so far we are mostly talking about convolutional networks. And through convolutional networks together with large-scale imagery dataset, we are able to learn good representations or filters for every recognition tasks. So it means that in image processing or before deep learning, we have been studying and manually crafted a lot of features and filters to extract important information for high-level tasks like object detection. With convolutional networks, we are able to learn to extract those representation and filters for the recognition task. And slightly surprisingly, convolutional network technique is also effective for low vision tasks like super resolution or some other image enhancement tasks. And overall, it seems that everything is learnable if you have labels or you have supervision. And this has become a gold rush for the computer vision research community during the past almost a decade. And it seems that we are still mining valuable stuff from this deep learning technique. And I have to remind you before we dive into various techniques. So although that we have seen a lot of work in those areas, but this idea of using deep learning for computer vision has only become popular within this past decade, even though it has been studied for a long time. And when you study, like in the previous lecture, when we study some other subjects, so we may have already studying them for like 20 or 30 years, and there has been a lot of good works that we know now, and they have sustained the test of time. But for deep learning methods, a lot of those, because they are just so new, most of the methods was invented during the past 5 years, and it's still not clear that which methods will stand test of time, and we just do not know. And maybe in 5 years, the whole lecture will be rewritten. But I'm sure that some of the core ideas that we are seeing in this lecture will be there and will influence the future development of computer vision algorithms. First of all, the deep learning lecture on supervised learning will review some of the previous lectures and also talk about the deep learning solution for those problems. And here is an overview, like which problem has been resolved by deep learning and which problems are still kind of mixed. For image enhancement, most of the current techniques are deep learning based. People are learning a lot of filters that can enhance the image much better. And very likely on your phone, when you take a picture, those low-level filters learned by deep learning are helping you to beautify your pictures. And at the same time, feature extraction has been largely based on deep learning if we are talking about feature for high-level recognition. And people has been very actively studying how we can use learning method to extract the features for low-level tasks. And but at the same time, features like SIFT are still there for finding pixel level correspondence or doing some SLAM or some other like 3D reconstruction tasks. And for texture synthesis or for image content generation, most of the methods has been based on convolutional networks now. And of course, if you want to recognize objects, you will have to use deep learning. And that's how the whole wave of deep learning started. And if you want to do find pixel correspondence across different images or across a pair of stereo image, then the state-of-art methods has been based on deep learning, either it's optical flow or stereo. And the deep learning methods has been able to improve the accuracy as well as speed up the algorithms significantly, sometimes even 10 times faster than traditional algorithm. And for 3D tasks, is the feeling is mixed. If we are talking about single image recognition, like track 3D bounding box or understanding 3D geometry information from a single image, then we will have to rely on deep learning or convolutional networks. But if we are talking about structure from motion or even non-rigid object reconstruction, then most of the techniques are still based on traditional methods. People are still using SIFT to extract the low-level features to build correspondence most of the time, and then using nonlinear reconstruction and use algebraic methods to optimize representation errors in order to get a good 3D structure from multiple images. And as you can see, when we have been comfortably using geometry methods to reconstruct 3D scenes, especially static 3D scenes, then most likely you will turn to traditional methods. But if we need to rely on some learning method or reconstruct from the input data where 3D information is ill-posed, like single image 3D reconstruction, then we will have to use deep learning methods. And in this lecture, we will focus on the recognition tasks. And we will start with simple image classification task. And some of the networks has been discussed in the previous lecture. But we will go beyond image classification and dive into semantic segmentation, which is a big gap. And we will talk about that in more details later. And then from semantic segmentation, we will talk about how we can have instance information to do object detection, and then combine object detection and segmentation to perform instance segmentation. And based on instance segmentation networks, how we can have fine granular information like pose estimation and 3D object detection, basically based on the object features and representation to estimate those detailed information. And beyond the image task, we will also talk about object tracking and also 3D object tracking. Okay, now let's talk about image classification. The definition of the task is very simple. Given an image, we want to predict what's inside the image, and usually the image only contains one major object, and then we will provide the label what that object is. And we have seen a lot of small datasets like Calcat11 and CFAR. Those datasets have been widely used in image classification, especially in recent research of deep learning. People have been essentially use CFAR to quickly test their ideas for new networks. And if you really want to show that your network can do something serious, then you will have to train your network on ImageNet. And the image in ImageNet are more complicated. And even though that each image has one label, there may be some other objects in the label as in the image as well. Okay, let's start with AlexNet for image classification. I'm sure by now you have already heard this network multiple times. That is the network that starts whole waves of deep learning. And you probably also have seen these pictures multiple times describing the structure of AlexNet. And here I want to highlight several interesting things in this structure that may also be interesting and discussed in the later work. So first of all, you can see that there are actually two groups of networks in this structure, there are upper part of the convolution and the lower part, and they share the same same parameters, not in terms of weights, but in terms of number of channels and the convolution's kernel size. And the reason they do that is to speed up the computation. They actually try to use two GPUs, and at that time it was GTX 580 to speed up the computation. And and the goal here is they want to delineate the computation of two halves of the network, and then only communicate when it's necessary, like here and here, so that they can achieve speed that is faster than only using one GPU. And later, there is a whole field of research study on how we can speed up the convolution networks on multiple GPUs or even across multiple machines. And there's another feature of this network that is it only has 8 layers. And at that time, it was probably the biggest network people have tried, for image classification. But by the current standard, this is definitely a small network. And therefore, with the success of this convolutional network, and people have thinking that what if we further extend the depth of network, can we get even better performance? And this is exactly what people did around those years. And people have been keep thinking like how we can train deeper networks, and whether deeper networks can bring us much better performance than AlexNet, even though it's already gave us some breakthrough performance. And there are several very successful attempts. One of them is GoogleNet, and they proposed this called the inception module. Basically, the hypothesis that within each layer or at each level, the network can be actually break down several pathways, and from the information of the previous layers, they can try to have one-to-one convolution layer, and also several 3x3, 5x5 convolution, and also pooling layers. And they also trying to add one-by-one convolution for dimension reduction, so that they can have some computation efficiency. And this basically based on this simple module, they built the very deep network that keep reusing this module again and again throughout the network. And one thing you can see here is this model is much deeper than AlexNet, and they actually encountered some difficulty in training the whole network from end to end, and therefore the solution they use is to provide supervision at multiple levels. For example, from the middle part of the network, they have one branch that tries to decode the information from this layer, and then trying to do a classification. They will put a classification signal softmax here, and use cross entropy loss with classification label, and produce back loss information and provide gradients to train the lower network, together with the loss at the end. And here you can also see that they use this again in the upper part of the network. In total, they have 3 loss throughout the whole network, and it means that theoretically those 3 heads can all produce classification predictions. But when after they train the network and use it for inference, they only use the final output. And at the same time, another attempt is called VGGNet, and the paper title is called Very Deep Convolutional Networks for Large-Scale Image Recognition. It's very straightforward. What is the goal of the paper? As you can see there, so after we have 8-layer AlexNet, now we have they are trying to gradually make the network deeper by using VGG 11 and VGG 13, 16, and eventually 19. And you can see that they use some scheme to control the increase of parameters so that the parameters do not increase significantly, but with the increase of the depth, the classification error keep decreasing. And they also encounter some problems when training the very deep networks. And the technique they use for training the deep network is they first train a shallow network, and so that they can get decent weights for for each convolution layer, and then they use this convolution layer to initialize the weights of the deeper network, and random initialize the new layers, and then train the whole network again, and then they use this trick again to gradually initialize deeper and deeper network until they can train uh, the biggest network they are trying here. And this network has become the backbone or the basis for a lot of follow-up work in semantic segmentation and object detection. And at the same time, people have tried a lot of different options, and but there are several tricks you can still find useful when you want to train your own network or try out some novel network structures. First of all, you may be able to use multiple laws that at different level of network, or you can use multiple head at the end of the network to jointly train the model. Usually, those multiple laws can produce complementary gradients to guide the training, and so that you can obtain some good weights for each layer. And people have also tried stage initialization, so that you can train the network layer by layer, or train or like VGG, so divide the network into multiple stages, and then gradually increase the number of layers within each stage. And of course, we have been using stochastic gradient descent to train the networks, and there are some standard parts in the gradient descent. For example, we use weight regularization and tune the learning rate. Essentially, stochastic gradient descent is one kind of gradient descent, and it all suffers or it will benefit from a wide choice of learning rate. And there are also momentum and data augmentation, that those has been discussed in the previous lecture, and people have also tried to do some smart initialization, and in the end, also people have also tried model ensemble, which means that say you have the network structure XNet or VGGNet, then you train multiple of them with different initialization. And say you have trained 7 model of them, and then when you want to classify one image, you average the classification probability from these 7 networks, and then find out that what will be the voting of probability for each class, and then find the most likely class from that ensembled probability estimation. So there are some questions for you to think about. And the first question here is, say you want to tune learning rate and momentum. So what is the relation between learning rate and momentum? They are all techniques that will affect the magnitude of your gradient. And the second question is, we are all using softmax as output of the network for and then put cross entropy on top of softmax as a loss to supervise the training, and then use the gradient to optimize the network weights. And here is a situation. Say you want to do a two-way classification, and then the input for the softmax is you have two values for the softmax. One is 100, the other is 1. What will be the output of the softmax operation from GPU? And the third question here is, what if your learning rate too small, say 10 to the power of -10? What will happen in those cases? By the way, normally the learning rate is a very small number, and for AlexNet or VGG, the learning rate start with something like 10 to the power of -3, -2, and it's always in a small range. And here the question is, what if the learning rate is very small? And after people have explored those network structure, and people have also turned their attention into different operations and try to propose new operations for the convolutional networks. And one very important operation is called batch normalization. It basically says that for each layer, we will renormalize the output of each layer so that they have a zero mean and the standard variance for the whole network. And they have a very long discussion about why this can reduce internal covariance shift. In the end, we find that with this normalization, the gradient can be propagated through the very deep network more successfully. So in the sense that if we use batch normalization in the GoogleNet, then we no longer need the multiple losses. We only need the loss at the end, and by propagate the gradient of loss to the beginning of the network. So with the previous elements, like the understanding that deeper network will likely yield better results, and use batch normalization, we can directly train the network with only one loss. Then we come to probably the most successful network called the residual networks, or ResNets. So the idea is very simple. We have convolution module like 3x3 and 3x3 or 1 by 1, and here each convolution is actually a 3-layer. The first layer is a 3x3 convolution, and then the second layer is batch norm, followed by a ReLU activation layer. And that's what's happening within each block. And then we put two blocks together, or 2 or 3 blocks together, and put a residual connection across the whole block. This means that the output of this block will be added with the input of the block directly, without scaling or anything. And then we find that this network structure can be used in training very deep models. For example, here is a comparison between a 34-layer ResNet with VGG19. And as you can see that they have very similar structure. For VGG, for the VGG net, we have several groups of layers, and each group downsample the resolution of previous layers with a pooling and a stride. And then within each layer, we just keep using the 3x3 convolution. And with the 34 plane network, it just means that having more 3x3 convolutions within each group. And when we introduce residual connections, it doesn't add much complexity to the network. We are only adding those residual connections, and as I mentioned, is add the input of the block to the output of the block. As you can see here, so if we look back from the output, there is actually a direct connection to all the previous layers. For example, all the previous layers, so that the output loss can be propagated directly to the very beginning of the network. That is the one secret of success for ResNet. so that it can automatically have multiple level of supervision, and this can that can make the gradient propagation through the very deep network much easier. And because of discovery of this receiver connection, and we can use it to train much deeper network. And here originally we were talking about 10 layer, 8 layer network, 19 layer network, but now we can easily explore 15 layer, 100 layer, and even several hundred layers of network. And you can see here they are all following the same pattern. The whole network is grouped into several levels, and within each group, we just repeatedly use the block to increase the depth of the network. And the residual network dramatically decrease the error of the classification accuracy. As you can see here, ResNet 50 achieve much better performance than the previous network. And then if we make the network even deeper, then we get a lower error rate. And people have also tried some variants of the network. For example, in this network called wider residual networks, we try to increase the number of parameters or number of channels within each level. And then I say overall, even if we have 50 layers, then it has same number of parameters with the 150 layers ResNet. But its performance is better, especially better than the network with similar levels, and it can also have slightly better performance than the deep network. And at the same time, because it's easier to parallel a wider network than a deeper network, and in reality, we also have faster computation time, even though that we have more parameters in the model. Another technique people have tried is to divide the convolution within each layer into multiple groups. So the idea here is the different groups may be able to learn independent representation, and when we put them together, they may become stronger. And also at the beginning of the input, we can do dimension reduction so that the computation for each symmetric convolution won't blow up. And with this grouping technique, we can probably improve the performance. But I want to point out that remember this group operation was actually also used in AlexNet, and at that time, that it was used for accelerating the network training. And it's interesting to see that after several years, we realize that it can also be used to improve the network performance. And with this grouping, so I want to highlight that with this grouping, then say if we have symmetric convolution, then its input dimension was dramatically reduced, and therefore even if that we may have more symmetric convolution filters, because each filter has a limited number of inputs, the total parameters can be reduced. And therefore, for example here, when we are using ResNet 50 and split the channels into multiple parts, say here, originally we have 128 128 channels, and then in the ResNext we can run 256 channels with 32 groups. And because each group convolution can have less parameters, the overall parameters can be similar with the original network, even though that we have more channels at each level, and it has same parameters and also similar computation flops. And this can theoretically we can achieve we can learn more representation, which is more output representation at each layer, but at the same time without increased number of parameters and theoretical computation. But in practice, say ResNet 50 can be slower than ResNet 50. And can you guess why that happens? So in any case, ResNet indeed improved performance compared to the original network. For example, if we are considering 50-layer network, then with ResNext, we can improve performance on ImageNet by more than 1%. And for the ResNet 1.1, it can improve performance by almost 1%. Even though that this may not sound very significant, that we want to emphasize that at that time the competition on ResNet is very fierce. So 1 point improvement on ResNet is actually on ImageNet is actually very significant, but it probably less so on the other datasets. And basically after 2012, the whole field, not just in computer vision, but in the whole machine learning, entered the gold rush of representation learning. And there has been crazy amount of research on what is the best network architecture that can to extract the representations from images and use them for various computer vision tasks. And basically everything is up to changing and tuning. So people may design new type of convolution kernels or different type of activation functions. And as I mentioned, people also invent Bayesian norm, which wasn't really available before that. And a lot of those parameters configurations has been exhaustively tried in order to improve performance and understand that the whole design space. And in the end, a lot of these trials become quite mechanical, and we do not know that whether what will be the end, whether we have really tried every combination. And since the whole thing is mechanical, what if we can let the machine to keep trying different configuration, and we only need to wait for the results? That brings us a neural net architecture search. It means that we have a lot of parameters we need to tune, or there are a lot of parameters that may be critical for the network performance. We can use search mechanism to try different combination of parameters and to see that how we can get better configuration and learn from experience that what will be the direction of configuration we want to we can try. And that for example, in this work, we make the parameter for each layer, like number of filters, a parameter, and the filter size is parameter. Then the goal is to optimize those parameters. We can use reinforcement learning to explore the whole parameter space. The basic process is we can have initial guess for a configuration, and we can have a probability representation for each configuration. Say we have a distribution for the filter height and a distribution for number of filters, and then initially we may have uniform distribution for different configuration. After we train the whole network, we will have a loss, and we will have a loss for the network itself. And the loss may be good or may not be, or it may be bad. But at this time we do not know. But we can do multiple trials and see that which configuration can give us better performance. Then we can get some clue that how we should tune those parameters. And this will also give the algorithm some clue that what will be the direction to continuously optimize those parameters. We can use the reinforcement learning techniques to learn from those past experience, repeatedly try new configuration and test its accuracy, and continuously find better configuration. And as you hear correctly here, Within each group of parameters, we train the whole network. It may take hours or for ImageNet when it may need days on one single GPU to try to train the network to the end and to find what will be the accuracy of this particular network configuration. For each trial, for each configuration, we will spend this much computation, spend that much of time to get the end result, and we keep trying new configuration. Therefore, the initial algorithm to do this architecture search can take thousands of GPU and multiple days to find the best configuration. Nowadays, people are doing better, but neural architecture search in general is still very computation intensive. So overall, because of the discovery of AxeNet, the machine learning field and computer vision, or even and the natural language processing, those sub areas in artificial intelligence put more focus on representation learning. And the story is never ending. So initially, before the popularity of deep learning, we have been spent a lot of efforts to manually design filters and extract features from images for correspondence and for object recognition. And now we can design network to learn to extract features, and our task is to design better networks, and probably sometimes to design different training laws. And further, we can use neural network search to learn how to design network. And this trend is just not ending, and it seems that we are just designing higher order of techniques in order to make our design work easier.